Okay. We'll talk more on Wednesday about the exam. So today we're going to march on to the next chapter of the class, of the course. So, but before I go talk about the specific concept, I want to have like another sort of open discussion on examples you may have encountered before. From there, we'll see what sort of thermodynamic principle we can derive from it. So this is going to be a little bit discussion, and I'm going to call people. Especially, I have a sheet of name that I haven't seen very often, so I'm going to try to call, see if you can join the discussion. So let's imagine we have a case where I have a big jar, and I seal this jar very well. So this is a jar. And then I have a beaker inside the jar. And here, I just have pure water. And I have another beaker. It's about the same height, but it's kind of beginning. Here, except that the water has a lot of concentrated salt in it. Obviously, the jar is fully sealed. So I'm going to ask people, like, if I wait long enough, what will happen to the level of the water on each of the beakers? Now, before you jump into join the discussion, I'm going to go for names that I have not really seen come out of class discussion. So, if I see your name wrong, just correct me, okay? I'm trying, since you haven't joined a lot, so I haven't called your name up. Chem432. Is that you, right? Yeah. Yeah, you actually talked once, so, but I'm going to try you on this. So what do you think will happen if I have two beakers in the jar that fully sealed, that the water in the two beakers are the same level? The only difference is one beaker has a high concentration of salt. The other beaker is just pure water. Now, I'll just let the two beakers sitting there. And this is actually not as intuitive of some of the things that we have talked about before, but it's something that some of you may be able to guess, or you may have a hunch for it. I'll hold on, I'm going to call. So, Chungya, do you want to give it a try? There's actually no worry about incorrect answer, because this is just talking about life experience. You can just say whatever. So there's three answers, right? One beaker is going to rise, one beaker is lower, and there's nothing going to happen, basically. Okay, well, let's show you. Nothing will happen. Good. That's well, just give it a thought. That's the whole point here, is that make you think, and then when you think a little bit harder, later on, if you find out it's slightly different, you make a stronger impression in you. So I guess that's why people want to create an atmosphere in class to encourage people to join the discussion.
What was the question again?
The question basically is, I have to, you know the situation described, right? I want to know what the level of the water will do. That they're going to change? Or the answer is not change. The other answer is one beaker water will rise, one beaker will drop. And Renee, I'm going to wait for you a little bit. I'm going to try to call other name first. Chin Yu Ling. Jerry. Okay. So then you doesn't count because you called. You speak a lot. So, but Jerry, why don't you go say it? See what?
I think the pure water level would be lower.
Okay. All right. So how do you figure that out? Have you ever really just experienced something like that?
No, but like, it's more, I feel like it's more logical for the one with water to be lower, because there's the concentration of salt. I don't know, it's just intuition.
Okay, so you kind of get it right, but I want to see if someone else can share the vision and give a more direct, like, guess what might be happening. The students behind, what's your name again?
Oh, Evan.
Evan. So maybe that's why in the register we all like Jerry. You have name that didn't show up in the register, so I got probably just called the name up. So you're Jerry. So Evan. So what is your? Jerry's answer is correct, but can you provide a explanation for why the pure water will drop, which also means the salt water will rise?
I think it's because to lower the salt concentration of the salt water, so the water will evaporate from regular water cut to the salt water. So it's like osmosis more.
You almost get something. You get a concept way too far ahead. We're not going to talk about osmosis at the moment, but we will use something we have learned so far. So Evan basically got it right. So, but now I'm going to go back to ask the class to join the discussion. Now, with all the things we learned so far, what is your best guess that how to explain this phenomenon? Come back to the phase diagram. I know Aaron already anxious to raise his hand more times. Go ahead, yeah, give it a try. It's open to the class, yeah.
Is it because of the intermolecular forces, meaning the vapor pressure and the vapor, like the vapor pressure of the one on the pure water is going to be higher than the one on the right because of the salt? It's going to keep the water trapped, so you're not going to go up.
Yeah.
And you're not going
Yeah, okay, so Aaron basically said similar thing to the osmosis idea. It was the vapor pressure difference. But the salt water has a lower vapor pressure than the pure water. So therefore, the vapor pressure higher one, the water will end up and just go into the salt. So the answer really is the pure water will drop the level, the salt will rise. But I still want something even more there, because the vapor pressure is not a general principle that we have discussed. I want another person to chime in the idea that what is the basic concept that we have discussed. To talk about when some substance move from one phase to another phase, what is the determining factor of a thermodynamic principle on a heat?
Maybe the entropy.
We all go around the box. We just don't go at it. Yeah, entropy is the underlying cause, but we actually have used a concept very frequently. In fact, I have tested you in the final question of the exam, and I made you guys think about it. Gibbs energy is still not quite there. There's not more behind it. And what Gibbs energy?
Change.
The
Difference
change of it.
in.
Yeah.
Yeah.
So the change, well, basically, when a matter is going from one place to another place, or from one situation to another situation, from one phase to another phase, or in this case, it can be anything. What doesn't really mean that matters what Gibbs energy is changing, or which one is higher or which one is lower. We use the concept of what? Not the total Gibbs energy, right? So how do we decide whether the water is going to melt in the ice when you step on it with high pressure? We don't use the total Gibbs energy, don't we?
Delta.
Use change, but
I mean, not delta. Yeah, D.
the molar per mole Gibbs energy, right? So this is something a little bit we try to. So there's something we have before. We used this thing quite often, molar Gibbs energy. So if we talk about a phase situation, phase 1 or 2, and when the equilibrium, the molar Gibbs energy equal, and if one guy is larger than, it's going to the down. So, Melissa?
I was just wondering if you were recording this.
Yes, I am.
Okay.
Oh, I actually realized that some of the important concepts that I'm guessing that later on you may want to go check it one more time. So, so I'm doing it now. And okay, so so this is something we have already discussed, right? Now here it gets us a very tricky situation. When we deal with the phase transition, we have a way to calculate the molar Gibbs energy by the total Gibbs energy by the mole. That's actually the molar Gibbs energy. And then from there, we use this quite frequently to describe whether two phases at equilibrium or one phase is favorably turning into another phase by comparing the molar Gibbs energy. Here, we have pretty much just looked at the phenomena where we have, some of you at least have a common experience, and you would guess. Some of you even use concept that you have learned in other situations like osmosis. We'll come back to talk about osmotic pressure after we set up all this. In fact, the osmotic pressure is in the end point of this discussion when we explain osmotic pressure using the concept starting from this, the very basics. Okay? Now, basically, we're getting to a point where, okay, for this one, for the pure water, the molar Gibbs energy is simple, right? The total Gibbs energy, that is more of the water, and we get it. But what about the solution of water? Obviously, we have the total Gibbs energy. I mean, let's just say this is total. And then we also have some more water. Let's say the number of water, let's just say they're approximately about the same, right? Because we just put a little bit of salt. The salt occupied a tiny amount of volume. It didn't really affect much. So I can say the total amount. The volume is the same. The total Gibbs energy is the same. But obviously, if we do the same thing, we already know this guy is different, right? So that basically created a situation that we want to understand when molar Gibbs energy is calculated in a mixture. How do we think about it? Because this real life experience already gave us a hint that when you have a mixture, you can't take the total molar Gibbs energy of that substance in that mixture divided by the mole. And that is the, in fact, some of the suggestion, like Annie, you say is due to entropy effect. That was the reason. Hopefully we'll see that your answer is correct, but a lot of you are ahead of me because some of you use osmosis. That's ahead of me by 6 or 8 weeks. Later we're going to, and he's probably 20 minutes ahead of me because we'll get to that point very soon. So, but the main point I want to illustrate using this example is that when we started to step outside of the pure substance phase equilibrium, we have seen that if you have a mixture, your Gibbs energy calculation per mole clearly has to be modified. Or otherwise, if in here we have the Gibbs energy and the total water didn't change much, we just sprinkle a bunch of salt and the water doesn't change, clearly will affect the molar Gibbs of the water. And to the point where the per mole Gibbs energy of the water in the salt is clearly lower than when it's pure. Right? So how do we think about this problem?
So you're saying you can't, like, for a mixture, we can't divide total Gibbs by the number of moles?
Correct. So Diego basically reiterated my point very well. That is, when you have a mixture, you can't simply take the total Gibbs energy of that substance and divide by the per mole in it. Now, we want to illustrate this using another very familiar system that we have discussed before. Now, let's hold on this for a moment. Let's think about something a little bit easier for us to model. Let's just look at what we have already discussed. Let's say an isolated system. Now I have a separation between the two. I mean, it doesn't have to be equal. So I have an ideal gas, A and B. And this guy was occupy a volume of VA, this guy gas BB, and the temperature of each side is the same. So now I'm actually separate. In this case, before I separate, of course, I have N molar of this gas and N molar of this gas. Of course, it's in this volume, also it's in this volume. So if I actually just try to make the picture even more indicative of what's going on, I can just mark the molecule different, just indicating they're different molecules. So if I actually calculate the Gibbs energy of each of this, I can say, hey, in the left side, the molar Gibbs energy, just like you normally do. So you would have the total molar Gibbs, total Gibbs energy of A divided by its molar, then you would get the molar Gibbs energy of A, right? And the Gibbs and total Gibbs energy of B, there will be the molar Gibbs energy of B. Obviously, the total of the system's Gibbs energy equals to the total what A and B can contribute. Then you can actually simply say NA, the molar Gibbs energy of A, and B, the molar Gibbs energy of Okay, this part should be straightforward, right?
Is B also an ideal gas?
Yeah, it's also ideal gas. So maybe I just put it over here. All right, so far, hopefully this is not very complicated, but let's do the experiment that we have covered before. Now we remove this separation barrier. So now okay, I try to draw as big as the same side, but you know what I mean. But so let's say about the same size, and then now accept the whole this gas that's moving around in the whole space, the other molecule also move around. So you have A and B totally mixed. Now, except in this case, of course, the temperature pressure is still the same because it started everybody's temperature pressure is the same. The total volume becomes VA plus VB. So clearly, you still have a Gibbs energy, right? The total Gibbs energy of the system. And clearly, in this case, you know you have that more of Gibbs energy of this ideal gas A, and you also have the molar Gibbs energy of A. Let's just for the moment, I'm writing down this. So, and then the B molar of Gibbs energy of the second ideal gas. Everybody still with me? Yeah? All right, so next question is, I didn't do anything, I didn't add anything, I just simply yanked the separation apart. So, Micah, you ready to chime in your opinion? So what do you think about the two Gibbs energy? Do you think they're equal to six? I mean, they're the same gas there. They don't go in. I don't lose any gas. I'm leaking out and nothing added in. What do you think about the Gibbs energy of the two situations? Okay, three possible choices. This is bigger. This is smaller. They're the same. Okay, you illuminated two wrong answer. So that's good. Well, one wrong answer. So you have to choose the other two because that's three. You got one out of the way. That's good.
So, I think the second one
Oh, you got, all right, good job, you got it, but now I'm asking you why.
I don't know if it's like right or not,
Yes, you're ahead of me, but I want you to know, so basically you're saying, so is this is smaller or bigger? Okay, good, so yeah, that's a good job. So so this guy is smaller, and it is caused by entropy, but that's again ahead of the game. I'm trying to answer, for a temperature pressure constant process, you know this process is spontaneous, right? If you yank this open, the gas is going to rush into each other. And they're not going to just spontaneously go back with all gas molecules, A stay on the left side, they don't do that. So you know this direction is going spontaneous. So using the Gibbs energy we have discussed, since like this, we kind of know the Gibbs energy must have changed. They can't be equal. If they're equal, that means they're equivalent, reversible, they can go back and forth. No, we know they don't come backwards. So we know something. So now, all of a sudden, we have to put this guy an asterisk or whatever, or a prime on it. We know they are not the same anymore, and we know this original guy, so this guy minus this guy is smaller than 0. Renee, I saw you raise your hand. I was trying to finish my discussion before I
Yeah,
go.
so, this was more of a thought process. I think I kind of answered it, but let's say if gas A and B, if they're both the same gas,
Yeah.
that equation would show just a little less of a change, right? Because it's
Oh yeah, if A and B is the same, then nothing's going to be equivalent. Then we'll also come back to that point. Then they're equal because you didn't, as if nothing that you didn't do anything, because they're the same molecule. So you did as if you didn't do anything.
okay.
Any other? We're all still on the same step? Still with me? Diego?
So A and B are different here,
Oh yeah, they are different.
but they were the same mean.
If there is, so we will get to that point actually quickly. So the A and B are different gas. They're different identity. If they are the same identity, then they're almost as if nothing happens. So we'll see that. Yeah, we're still together. So now so our next job really is trying to figure out what is the difference of the two. What made these two different? So when I yank the separation over, it's clearly the gas start mixing, and as a result, I know the total Gibbs energy after you remove the separation has decreased. That corresponding to the principle we have discussed. Explain the process to be spontaneous, or they cannot go back by itself, right? Now, our job is trying to figure out, is there any way we can calculate the difference based on what we learned before? I think, Annie, you mentioned entropy. So basically, our intuition base says the biggest difference between these two is one, the entropy of this guy was higher. They are more disordered. So that's a good clue how we figure out this. So let's just say we call this delta G of this process, right? And basically is after the separation and is removed, and this is before, and there is a Gibbs energy change. And we kind of already know that the Gibbs energy change probably is caused by entropy, so we have to kind of get to how the Gibbs energy is changed, or change here is related to entropy. So what equation should I use? How do I relate? So if I can, delta G equals to, what was the changing of Gibbs energy relationship to the entropy change by the equation where we have covered before. Diego?
H minus Ts.
Yeah, so H minus, so, and here also the delta. Yeah, so you said that the definition, and he basically said you use delta. So let's try to figure out something from here. But obviously this delta H here is kind of in the way. We don't want this to be interfering our goal. Our goal is trying to, we know we can calculate this, but so what about the delta H here? Nick?
It's 0.
Why?
It's isothermal process.
Okay, so that means you probably answered the first question correct in the exam. So there's a delta H and delta U, they're both equal to 0 because the temperature is the same. Okay, good. So we're getting somewhere. That's nice. So, okay, that means we just need to figure out what the delta S is, because you know this is something that we want to do. So basically, that means our job is figuring out what delta S, and in this case, is virtually delta S mixing. We kind of touched upon this earlier when we talk about the entropy. There's 3 classical example of entropy, right? We explained gas expansion. We explained the object hitting a mix at peak temperature. And the gas expansion, another example of it is when you have 2 gases expand to each other. I guess that's maybe what you were trying to do. So, anyone can tell me very quickly how do we figure out the delta S mix here? This is when your cheat sheets become very useful. But if you don't remember your cheat sheet, just say the general concept. What is the entropy of mixing in this case? Anything?
Since it's a state function, if we treat each gas as if it was isothermal expansion,
Yeah.
we can find the Q by integrating, so NR T11
Okay.
B2 over B1.
Yeah.
And
So
then we can divide by.
yeah. So that was the question in the old exam, the sample exam. So I'm sure you studied, so I'm not going to repeat here, but the whole idea is, and he explained earlier, is that you can think of, is this gas expanding to a bigger volume, or this gas expanding to another volume? I'm going to skip all this, and then he said, if you are wondering about it, you go back to see the lecture notes, and you also see the answer key to the sample exam. I forgot which question, it was question 2 or 3. So the whole idea is, for gas A, its entropy increased by expanding from its original volume to a bigger volume. So I'm just going to write it out. And gas B also just think about each gas had more place to go. That's basically I mean, how do we get there? You want to go back to see the old notes, okay? Now, obviously, we can actually make this a little bit the common convention I want to introduce right now. Because when we talk about mix, we don't necessarily like to use the volume a lot. We tend to use the percentage, right? Sometimes you say, hey, 5% of something by weight, or sometimes in this case, we use a lot more molar fraction, quite a bit. And that's something that we will introduce. So you'll see pretty soon, very quickly, why we do that. It will become very convenient. But per se, just using this concept, you already know that delta S equals delta SA plus delta SB is larger than 0 because each of the term is larger than 1, right? So when we come back, we already answered the question, why delta G become a negative? Because this is positive, that's 0, T is always positive. So we sort of answered the question qualitatively. So should be no surprise why now the G prime total, that is the system in this state, its Gibbs energy already is lower because the delta S A and B both are positive, so the total delta S is positive, And this time together positive, then that's negative, then the delta is negative, that means this guy's smaller. Everybody with me? I mean, that's a whole long, a mouthful of multiple sequence there. Good? All right, so now I want to expand this a little bit more and introduce a concept that we're going to use on pretty much the rest of the semester. That is, today's lecture, the reason I also tape it is because it introduced the most frequently used concept, and at the end of the lecture you will see. So here I can, again, I'm not going to go over, but if you can just say P, V, A, N, A, R, T, and P, V, B, N, B, R, T. So as you can see, at constant temperature and pressure, the volume and volume, they're just proportional by saying constant, right? Everybody. So I'm not going to write out, but you see this, and pretty much this can be write out as R natural log NA plus NB, NA this NA plus NB NB. So everybody with me on this one? Good? All right, so actually the molar fraction is defined, and we'll use that a lot when we describe mixture. By, for example, the molar fraction of A in this mixed gas is basically what its molar accounted for the total mole of ideal gas. B virtually is NB. Right, so this is something we use quite a bit later on. So now we can see. So basically, this is a flip up of the molar fraction. So still with me? This is okay. So now basically the total delta S will become delta S A. S B, it will be natural log. I have made some mistake. I dropped a sums in here. So there is there's a molar in front of it. So okay. So what I'm trying to get here, hopefully will become very apparent once I plug all things together, and then you will see the point I'm trying to make here. So virtually the delta S is become, you can actually flip this over as a negative, because this 1 over x is, this itself is a fraction, right? So you can flip over, so basically you can. Everybody still? Well, if I write something wrong, also point out to me, because when I go too fast, and because I skipped over here, when you actually go plug in the equation, you will realize there's actually molar in front of it. So I'm not really quite talking about the molar, I would say, at the moment yet. So, so basically the total delta G would be the G prime, basically the one after you mixed, with the G before you mix, and that's delta H minus T delta S. Now delta H is 0, so therefore the T is negative in front of it, so I can put it T delta S minus NA log XA. So you can pretty much write. So I'm actually means this one, I replaced this. So I'm going to probably just, instead of confuse you, I'll put this in here. Like that. So then you, the negative will be NA RT plus NB RT. Yeah, I'm trying to slow down because I know I'm sometimes running fast, but I want to let you kind of look at it. Does this make sense? It's not all about trying to copy on the equation because I'm taking it. I have it on the PowerPoint. I want you to think along with me so that we can actually digest what this really means. Because right now it's all about a bunch of mathematical maneuver, but soon you'll see this is actually quite dramatic once you see what's going on. So here I can go G, the total must be equals G total plus NA RT natural log XA NB RT natural log. Okay, here I'm almost there. Probably I should come down in this side because my backboard usage is not the most organized. So, but remember this one can be expressed, this is pure one, right? So it itself is NaGa. This is when it's pure. So I can put a little asterisk indicating it's pure. And plus NBGB, and it's pure, right? So basically now in the mixture, the Gibbs energy of the total will be NaGa when it's pure plus NaRT is molar fraction. And then NB, that's molar Gibbs energy. Molar Gibbs energy B when it's pure plus NBRT. Now, this is the most important concept that I would like to arrive, and then we can drill in a little bit on this one in terms of what this equation really means. And then I'll conclude by saying the new chemical concept I would like to introduce today. So you almost can get a feel for what's going on here. That is, the fact that we're mixing two different matters together, they interfere each other's Gibbs energy. So clearly, molar Gibbs energy's definition is per mole of substance you dump into a system, you increase the Gibbs energy. So obviously, if you have a pure substance, you add one more, you increase the molar Gibbs energy by whatever amount. But the weird thing is, if you add one more to a lot of other stuff around, the whole thing gets diluted so much as if you didn't add anything. So that's what this equation really means. So that is the molar Gibbs energy contribution to the total Gibbs energy really depends on whether there's something there already mixing things up. Now let's see whether the statement I made any sense if I look at the equation here. Let's assuming there's no B around, and this is also equivalent of saying the gas is the same. So there's absolutely nothing. So this A obviously is 1, correct? Right? Because the molar fraction is 1. So that is, if I have a gas chamber, the majority is just A. Of course, every new molar of A I put in increase the molar Gibbs by per mole of whatever the pure molar Gibbs energy. Make sense? Yeah. Now, if I have a chamber, its majority is B, I put a trace amount of A there, you might say you can't even find your A, because it's all get diluted. You don't see them. That's when A is such a big negative. And of course, B would be almost close to 1. Then if you dump into any A in there, it's as if you didn't dump anything in. Makes sense?
Can you repeat that?
Okay, that's critical here. Now, where should I repeat stuff from? Should I start from the pure one? Okay, I'm focused on A at the moment. If at the beginning I have a chamber full of A gas, if I dump into one more A gas in, I increase the total Gibbs energy by per mole, the molar Gibbs of the pure A. We all good on that one? But in a chamber, the majority of them are gas B. That's what the B is big. This is trace amount. And then this is a gigantic negative term. Okay. Now I'm trying to dump into A, and do I increase the total Gibbs energy by the same amount of when it was pure? Definitely not, right? Because this thing is so big negative, it overrun everybody. You can think of this could be 0.00. So you can think of it as infinite. You can almost think like, I'm going to try to increase the molar Gibbs energy of S system. But if that system is pure, there's no question. We have no dispute. Whatever that I put in is the molar Gibbs energy times whatever the more I put in, okay? But if the system is a bunch of other stuff already there, if I try to put more of my gas into there, because of this entropic dilution, my contribution total Gibbs energy is minuscule. Make sense? I know because we actually, you know, if we did a little bit of this by partial derivative, so then we all agreed that we want to abandon the partial derivative for the moment, but it's actually virtually it's a partial derivative. So what this really means, so I have to really use this term a little bit. So basically in a mixture, the Gibbs energy of the total for a particular substance in it, when the other substance amount is fixed. This is what I'm trying to talk about. So when the other substance B component is fixed, and then when I try to increase a tiny amount of A, how do I affect the total Gibbs energy? That's the discussion we're making here. And the point here, this equation tells us that it really depends on the situation you are in. If you have a substance that's close pure to the sense you try to add in, that is the molar fraction close to 1, then this whole term is almost 1, and that is negligible, the other guy. So then this whole thing, per mole of Gibbs energy you put in, you contribute whatever the molar amount you're adding, right? Because this term does not cancel it. So that's basically what we're trying to convince you here. So we may have to come back to talk about a little bit more, because let me try to go back, summarize. The main point here today is we start by using a common experience to show that the molar Gibbs energy concept we have introduced earlier to describe pure substance equilibrium phase diagram. We can use the molar Gibbs energy to describe equilibrium or phase movement. But we have seen that when you have a mixture, the molar Gibbs energy can also be used to describe this phenomenon. But we are aware that because of this phenomenon, it tells us the molar Gibbs energy of a substance when it's in the mixture is different when it's pure. Make sense? This already tells us the water in the salt, its molar Gibbs energy is lower than when it's pure. That gives you everything is the same. Now that is just sort of intuitive observation. Now here, we try to use ideal gas to prove this point quantitatively. Now the main focus here is we show that when you mix two ideal gas on the same temperature pressure, the main reason that the Gibbs energy after the mixing is smaller is due to the entropic effect. So we have discussed there's no entropy effect, temperature pressure is the same. Now the entropic calculation led us to this intriguing phenomenon. That is, we discovered that the reason that after mixing, the total Gibbs energy is lower than the previous Gibbs energy because for every substance, the Gibbs energy deviate from its pure by the molar fraction. So you can think of, for the gas A, when it was pure, its per mole Gibbs energy is expressed by this. But when it's in the pure, its contribution to the total Gibbs energy has been discounted by this RT natural log XA. That's the entropic effect, which is what you said earlier. And so this whole reason that Gibbs energy lowered is because of the entropic reason. And as a result, the molar contribution of Gibbs energy per substance to the total Gibbs energy deviate from it when it's pure by this term. So it's for the B. Okay, so this basically is what we want to call them. So in the mixed point, the contribution of per mole of particular gas to this total Gibbs energy, of course temperature pressure is fixed, is defined as chemical potential because it will be so useful. So from here on, we'll start to not using molar Gibbs energy much more. So the answer to this question next time after you're taking Chem432 is that, oh, chemical potential of the water in the pure water is higher than the salt we've done. And then when you go around, you'll see many such examples when we predict if something's going to happen or something's going to flow from point A to point B or from phase 1 to phase 2, you simply compare the chemical potential of that substance, which can also be used to explain the osmotic pressure and other things that we'll be discussing later on. Okay, so that will be the end of today's discussion.